know, he said that he was going to be gone for the rest of the week.
All right, so questions. So I moved your homework yet again, so it's due Monday instead of Friday, because some of the stuff we're going to get through today, but then you don't have a chance to ask questions before Friday. So, so homework will be due Monday, but again, I'm going to ask you to try to work on it after today's lecture and then ask questions on Friday about the homework and then write it up over the weekend and turn it in. My focus is not great here. That's really annoying. All right, well, we started talking about the Pigeonhole Principle on Monday. And the basic setup was, if you have 4 buckets and you have 5 objects, however you decide to put those objects into buckets, at least one bucket will have at least 2 things in it. Okay, it's possible I could put 3 objects in here and 2 objects in there, in which case some bucket will have 3 objects in it, right? But however you put these things into these bins, it's not possible to have only 1 or 0 objects per bin. Somewhere there's going to be a bin that has at least 2 things in it. And it could have more, but it's got to have at least 2. So that's the essence of the Pigeonhole Principle. So let me give it to you in the kind of math speak sort of way. So if k is an integer and it's positive, bigger than 0, and k plus 1 objects are placed into k bins, at least one bin has 2 or more objects. In it. That's what I just said, except I threw some fancy z's in there, so now it looks like math. So examples. If you have 27 people, at least 2 have the same first initial. Assuming that initials are made up of the letters A through Z uppercase. So how do we get this with the Pigeonhole Principle? Make yourself 26 bins, label them A through Z, and take each of your 27 people and put them in one of these bins based on their first initial. And if any bin ends up with 2 or more people in it, it means those 2 or more people share the same first initial. And the Pigeonhole Principle tells us we have 27 people, 26 bins, and we're putting those objects into those bins. At least one bin is going to have 2 or more objects, which means at least 2 people are going to have the same first initial. Okay, 10-point quiz, and you have 11 people in the class. So how many possible grades are there?
10. Or 11.
It's actually 11.
Yeah,
because you can get a 0 or you can get a 10. So if you have 11 possible grades and you have 11 people in the class, it's possible that everybody could get a different grade from everybody else. But if you have 12 people in the class, you're guaranteed at least 2 people got the same grade. How? Use the pigeonhole principle. Make 11 bins. Place each person in a bin based on the grade they got. You've got 12 objects going into 11 bins. You're guaranteed at least one bin has at least 2 objects. And whatever grade corresponds to that, you know at least 2 people got that grade. One more example. Given any 8 people, at least 2 were born on the same day of the week. Right? There's only 7 days of the week. Make your 7 bins based on those 7 days, and you're putting 8 people into bins based on the day of the week they were born. So somewhere at least 2 people will be in the same bin. They were born the same day of the week. So there's nothing really startling going on here. Wow, that's really like fuzzy, man. I know how to fix it, but I don't want to take time. I'll fix it at the break. All right, so that's the pigeonhole principle. And obviously, if you have more than k plus 1 objects, if you have k plus 5 objects, you can put the first k plus 1 objects into bins and apply the pigeonhole principle, and you know that at least 2 are in one bin. And now if you add additional objects, right, you're just going to possibly add more things to the bin. This is actually true for if you have at least k plus 1 objects. Or if you have more than that, the pigeonhole principle still applies. Well, we can use this in some unexpected ways. So here's a theorem. For any positive integer, I'll call it I, there is some multiple of I that can be written with just ones and zeros. Written in decimal, not binary. So the number 1 is itself written as just a combination of ones and zeros, so that's fine. The number 2, if we multiply by 5, we get 10. That's written with a 1 followed by a 0. That's fine. What about the number 3? Is there a multiple that can be written with just ones and zeros? $1 million.
111.
Yeah. So 3 times 37 is 111. So that works. 4 has a multiple. 4 times 25 is 100. 5 times 2 is 10. 6 times something, this will also work. So this is true, but we'd like to prove that it's always true. And guess what? We can do this using the pigeonhole principle.
Wow.
Yeah. And we can make it really fuzzy. Oh, it was good for a moment. Hey, that's not bad. Okay. So how do we do this using the pigeonhole principle? This is really weird. This is not something I would expect you to come up with during an exam. It's just one of these things that's cool to see because somebody's already figured it out. Okay, so I is our positive integer. So let's look at the following numbers. So I'm going to look at the numbers 1, 11, 111, 1,111, 11,111, 111,111, and so on, up to the number containing I plus 1 ones. So if I want to do this for 6, I would just go from here up to 7 ones. So 1,111,111. Okay, now write each of these modulo I. So how many possible values can something, how many different values do we have when we write what things are congruent to modulo I? How many different possible answers can we get? Yeah, if we're writing things modulo 5, everything is congruent to either 0, 1, 2, 3, or 4. 5 things. If we're working modulo 3, everything is congruent to either 0, 1, or 2. 3 things. If we're working modulo I, there's only I possible congruences between 0 and I minus 1. Right? So make I bins. This is congruent to 0. This is congruent to 1. This is congruent to 2. This is congruent to I minus 1. So there's our I bins. And we have I plus 1 numbers, and we're going to place them into these bins according to their congruence. What's the pigeonhole principle tell us?
Some of them have to double up.
Some of them have to double up. There's at least one bin that contains 2 numbers of this form. All right, so from the pigeonhole principle, at least 2 numbers are in the same bin. So let's just call these 2 numbers A and B. Well, if they're in the same bin and this bin is bin K, that means that A is congruent to K and also B is congruent to K. So what can we say about A and B relative to each other? They're congruent to each other. Because this means that when we divide A by I, we have K left over. When we divide B by I, we have K left over. They have the same remainder. So A and B are congruent to each other, which means their difference is congruent to 0. Which means their difference is some multiple of I. So there are 2 numbers in this form that are just written as a succession of 1s whose difference is a multiple of I. So let's just suppose that A is the larger of the 2 numbers and B is the smaller. Then A minus B is going to be a multiple of I, and A minus B is going to look like a difference like this, which is going to be a bunch of 1s followed by a bunch of 0s. And that's a number in the form that we're requiring. So this number in particular will be a multiple of I. It'll be I times whatever that J is. And it's entirely a non-constructive proof. But it does give us a way to systematically find what multiple of 6 satisfies this property. So we can do this pretty quickly. So let's write our 7 numbers. And let's look at these mod 6. And I will happily cheat. So 1 is congruent to 1, 11 is congruent to 5, 111 is congruent to 3, 1111 is congruent to 1. And I can actually stop right here. I could keep going, but I know that when I do this, I'm going to have a repeat. So I'm going to have 7 rows, and each row is going to have a number between 0 and 5. There's only 6 possibilities. But I actually found a repeat right here. These two things are both congruent to 1. So if I subtract, that's got to be a multiple of 6. So 1111 is 185 times 6. Right, so I just found these congruences, and eventually I was guaranteed to find 2 that were congruent. Take their difference, that's a multiple of 6.
So those is the battery number?
Say what?
Is that the battery?
So that's the number that's composed of just ones and zeros. That's a multiple of 6 in this case.
Now, putting it this way, it's only going to find you numbers in the format of n1s followed by n0.
Correct, yeah.
Find any of the mix.
It won't find any of the mixes. And there's definitely ones, there's other ways to find this usually. So that's a weird application of the pigeonhole principle, right? Nothing to do with pigeons, but it works. All right, and so there's a generalized pigeonhole principle. And we need to define this operator. So this is sometimes called a ceiling function. So this funny symbol r equals the smallest integer bigger than or equal to r. Okay, so here's the generalized pigeonhole principle. If you have n objects and you have k bins, so given n object and k bins, then at least one bin has the following number of objects in it. It's the ceiling of n over k. So in our particular pigeonhole principle, we had k plus 1 objects in k bins. It tells us we have this many objects in at least one bin. And the ceiling of k plus 1 over k is 2. Right? It's slightly bigger than 1, so the smallest integer bigger than or equal to this is going to be 2. So if you apply this to k plus 1 objects in k bins, you just get the specific pigeonhole principle. But in general, we can double up and see things like this. And the ceiling function is a little peculiar at first. So the ceiling of 1 is 1. The ceiling of 1.001 is actually 2. The ceiling of 1.9999 is still 2. You go up a little more to 2, the ceiling of 2 is 2. And then the ceiling of 2 and just a little bit beyond 2 gets you to 3. All right, let me show you one more weird application of pigeonholes. So given n plus 1 positive integers, all of which are less than or equal to 2n, at least one is a multiple of another. So for example, n equals 10. It says if we pick 11 positive integers less than or equal to 20, at least one is going to be a multiple of another. Let me do n equals 5. We'll make it So 6 integers less than or equal to 10. So, well, I definitely don't want one of my integers to be 1 because everything is a multiple of 1. So I could pick the integer 2, and now I can't pick any multiples of 2. So I could pick 3, I could pick 5, I could pick 7. I need 2 more integers. I can't do 8 because it's even. I can't do 9 because it's a multiple of 3. I can't do 10 because it's even. So that won't work. But I could skip the 2 and I could start with a 3. Now I can do 4 and 5. I can't do 6, but I can do 7. Can't do 8, can't do 9, can't do 10. I still only got 4. And you can try this with different values of n, and it's really hard to get n plus 1 positive integers where none is a multiple of the other. But proving that is not something that's obvious how to do. But we can do it with the pigeonhole principle. So let me show you a quick proof for that. So let a1, a2, all the way up to an plus 1 be your integers. And they're all positive integers, and they're less than or equal to 2 times n. So factor out the largest power of 2 you can from each one. So write a sub I as 2 raised to some number, exponent sub I, times some q sub I, where these q sub i's are going to be odd. So factor out the biggest power of 2 you can from each of your numbers. So a1 is 2 to some exponent e1 times some odd number q1. a2 is 2 to the e2 times some odd number q2. an plus 1 is 2 to the en plus 1 times q n plus 1. And all of these numbers are odd. Well, how many odd numbers are there between 1 and 2n? There's n. So if n is equal to 1, how many odd numbers between 1 and 2? Just 1. If n is equal to 2, how many odd numbers between 1 and 4? 2. 1 and 3. If n is 3, how many odds between 1 and 6? 3. 1, 3, 5. And we could prove with an inductive proof there exist n odd numbers between 1 and 2n. But here we have n plus 1 odd numbers, q1 through qn plus 1. Straightforward pigeonhole principle tells us that at least 2 of these numbers must be the same. And whichever 2 of these numbers are the same, the corresponding a's differ just by having a different factor of a power of 2. So pick the number that's smaller, and the larger number is going to be the smaller number times 2 raised to the e2 minus e1. And so that larger one is a multiple of the smaller. In fact, it's a multiple by a power of 2. And so that proves your original assertion. It takes more math stuff to make that rigorous, but that's the intuition behind it. So pick your 2 numbers that have the same q, and the smaller one will go into the larger one an integral number of times. All right, so pigeonhole principle. The main trick in doing pigeonhole problems is figuring out how to translate what you're asked to do into buckets and balls, right? Objects and bins. You're trying to do something about people's birthdays, so you make a bunch of bins that are labeled with different birthdays, and the people are the objects you put into those bins, that kind of thing. These last few examples, don't worry about how to come up with that, because I have no idea. But usually the questions are more straightforward, and there's some homework questions on Pigeonhole. All right, good? All right. Last subject here, permutations and combinations. So definitions, a permutation is an ordered arrangement of objects. So when we talk about a permutation of three objects, we're talking about a particular ordering of those three objects. So I've got a pen, a marker, and an eraser. There's a permutation of it. Okay, marker, eraser, and pen. This is a different permutation. This is a different permutation. An R permutation is an ordered arrangement of R objects. So for example, here's a set of three elements A, B, C. Okay, this is a permutation of the elements in that set, A, B, C. This is another permutation. This is another permutation. This is another permutation. This would be an example of a two permutation of the elements of that set. It's an arrangement of two elements. This is a different two permutation. This is a different two permutation. And we're mostly going to be talking about how to figure out how many permutations there are of a collection of elements. Total permutations or R permutations. And a lot of problems can be translated into this question of how many permutations are there. So let's look at an example. You have 5 students. And you want 3 of them to stand in a line. Let's make it a Q if you like 222. So you're picking 3 students out of 5 to stand in a line. And in a line, the order matters. It's going to be somebody who's first, somebody who's second, somebody who's third. And the question is, how many ways can we have these students line up? And we can answer this using the product rule. So our task is to have 3 students go stand in a line. Let's break it into 3 subtasks. Task T1, pick student to go into the line first. T2, pick a student to go into the line second. And T3, pick a student to go into the line third. So how many ways can we complete task T1? How many ways can we pick a student to stand in the front of the line? 5 ways. How many ways can we then pick a student? Then after we've done task T1, how many ways can we pick a student to stand in the next place?
4.
Only 4, because we've already used 1 student. And task 3, we can do a total of 3 ways. So the total number of ways we can do this is 5 times 4 times 3, which is 60. So the number of 3 permutations of 5 objects is 60. So we have a formula, shorthand for writing this. We can write P parentheses N comma R. And this means the number of R permutations of N objects. So we just saw that P of 5 comma 3 equals 60. All right, well, we can generalize what we just did with students standing in a line. Suppose we have n objects to choose from, and we want to pick r of them in a particular order. So how many ways can we pick the first object? Total of n. How many ways can we pick the second object, n minus 1? How many ways can we pick the third object, n minus 2? How many ways can we pick the rth object? And that'll turn out to be n minus r minus 1, which is also n minus r plus 1. And so the total number of ways we can pick r objects out of n is just the product of this. So it's n times n minus 1 times n minus 2, all the way down to n minus r minus 1. Well, that's a bit of a pain to work with. So let's rewrite this. So n times n minus 1 all the way down to n minus r minus 1. Let's rewrite that as So I'm just going to multiply that expression by 1, but I'm going to write it in this peculiar form where I keep multiplying smaller and smaller numbers on top, and then I multiply the same smaller and smaller numbers on the bottom. So let me show you a specific example. So 5 times 4 times 3, I'm writing as 5 times 4 times 3 times 2 times 1 divided by 2 times 1. So don't worry about the r minus 1, r plus 1, all that stuff. We're really just expanding this top part to go all the way down to 1, and then putting that same extra piece on the bottom. So we're multiplying by a fancy version of 1. But if we do that, this upper part ends up being n factorial, and this bottom part ends up being n minus r factorial. And so this is going to be our formula for the number of r permutations of n objects. So it's n factorial over n minus r factorial. And it's nothing more than the product rule, but it's a more convenient form where we don't have to keep thinking of subtasks and values for big N and so on. So now we can just go crazy. So you have 10 runners, and we have 3 medals. So you got gold, silver, and bronze medals. How many possible ways can those medals be awarded? So somebody's going to be selected from these 10 to get the gold, somebody's going to get the silver, somebody's going to get the bronze. So the question is, how many ways can we arrange 3 people out of 10? So this is just the number of 3 permutations of 10 objects, which is 10 factorial over 7 factorial. Which, if you multiply it out and you cancel everything, it ends up just being 10 times 9 times 8, which is 720. And this, of course, is just the product rule sneaking in again. 10 people we can choose from to get the gold, and then 9 to choose from to get the silver, and then 8 to choose from to get the bronze. right? You got 6 people standing side by side for a picture. How many possible pictures can you come up with? How many different ways can you arrange these 6 people side by side?
6 actually.
So yeah, we're trying to find an ordered arrangement of 6 people taken from a set of 6 people. This is the number of 6 permutations of 6 objects, which is 6 factorial over 6 minus 6 factorial, which is 6 factorial over 0 factorial. What is 0 factorial?
1.
Don't you hate saying that? But it's true. So this is just 6 factorial, 720. Yeah. So how many permutations of A, B, C, D, E, F, G, H contain ABC somewhere inside? So we want to rearrange these 8 letters, but we know that when we rearrange them, we want A, B, and C to be next to each other. So how many different ways can we rearrange A through H such that A, B, C are next to each other? And if we think about it the right way, it's really easy.
Wouldn't it just be 8 factorial over 8 minus 3 factorial?
Why?
Take out the 3 characters to make it so that's not probable to have them scattered.
Okay, but then you still got to put them in somewhere.
It's true.
Yeah.
Can we just change ABC to just be one variable?
There you go. So let's just think of permutations of A, B, C, D, E, F, G, H. So now we got 6 things we're just trying to rearrange. And so this is just P6 comma 6. And again, it's 720. And this is common in these problems. Sometimes it's all about how you look at the question. Right? And this to me is very maddening about this subject. Because if you don't see it right, you can get there different ways, and sometimes it's sheets of paper. So why is 0 factorial equal to 1? Anybody know?
I assume it probably has to do with approximation. So that's what you looked up.
That was a red herring.
Ah.
Has to do with something called the gamma function. So gamma function is this definite integral from 0 to infinity. Gamma z is x to the z minus 1 e to the minus x dx. Take that integral from 0 to infinity and you get the gamma function. It's a weird function. But it's defined pretty much everywhere, and if you look at it on positive values, it matches factorials when your argument is an integer. It's actually off by 1, so gamma n is n minus 1 factorial. So if you want to find 0 factorial, all you got to do is find gamma 1, and gamma 1 turns out to be right here. It's equal to 1. So that's one argument that suggests 0 factorial should be 1. The other thing is it makes things like combinations and permutations work out really nicely. But this is an interesting business when you have a function defined on, say, just integers, but you have another function that matches it on integers but is also defined elsewhere. Is it really the same function? And maybe it is, maybe it isn't, but in some cases you can say that this is the only possible function that's defined in other areas but also matches this thing where factorials is defined. So that's something called analytic continuation. And this gets you into weird things like the sum of the reciprocals of all integers is equal to negative 1/12 or something like that. You can find a number file video on that. But this is a cool function because it's not defined at negative integers. It blows up. Sometimes it blows up to infinity, and sometimes it blows up to negative infinity. And it's asymptotic at these, and it gets flatter and flatter as you go to the left. But then over here to the right, it's got this nice factorial behavior. And you can get that relationship pretty easily using calculus if you do some tricks to find this, this integral. So there's tons of things you can do with the gamma function. So a good way to lose yourself if we get a snow day. But anyway, so yeah, we just take 0 factorial to be 1.
Does it have to do with, so like a factorial is just like 5 times 4 times 3 times 2 times 1. You don't multiply it by 0, but the
Yeah.
constant that you do multiply them is like the distance between the previous number on like the number line.
That might have something to do with it, yeah.
So like 0 factorial would, like, 1 factorial doesn't multiply by 0, but 0 factorial would probably try and multiply what's behind it, and then that has to do with it trying to look at the distance between 0
Yeah.
and some integer either in front or behind 0, which should start looking like 1 value. So
Yeah,
here's-
which is a little like if you were to code this, you'd have a running product. Would you initialize your product to 1, right?
Yeah.
And then you multiply that by successive integers up to and including n. Well, if n is 0, you don't multiply it by anything. You just have your 1 that you initialize to.
But
Kinda
the
the
distance
same.
on the number line between 1 and 0 is the same distance as
Yeah.
0 and some other integer smaller than 0. And
Right.
so 1 factorial is 1. 0 factorial is also 1 because it's traveling a total distance of 1 on the number line.
So what about negative 1 factorial?
We don't do negatives.
We don't do negatives.
Yeah.
It's
Yeah.
not like physics where somehow they magically made it so there's no weird asymptotic breaks when you start putting like
Right.
fractional masses or negative masses or
Yeah.
weird stuff like that. Somehow
That is a thing, though.
I mean, it messes it up like further on, but Newtonian was always fascinating to me because like, how do they get all these functions to work where they don't blow up when you start dealing with fractions?
Right,
or
right.
negatives? It just works.
Let's do a 5-minute break, and then we'll talk about combinations. KVL, KCL works with complex numbers,
Yeah, I know
which
you
is